Hello, scholars, and welcome to Chapter 10. Chapter 10 is all about sequences, series, and probability. So we're going to dive right in, and first of all, what is a sequence? A sequence can either be arithmetic or geometric. A sequence of numbers, you can see the ones I have down at the bottom. Here's a finite sequence, 0, 1, 2, 3, 4. Infinite, 3, 6, 9, 12, 15, and so on. So this sequence has 5 members. This sequence has infinitely many members. An arithmetic sequence, those are the two that you see below. They have a common difference. And later in the chapter, we'll also see a geometric sequence. They have a common factor. So, finite, infinite, arithmetic, geometric. A sequence can be described with a given rule. A given rule. That's the word we're looking for there. And here's a given rule. Consider a sub n. A sub n is 2 times n minus 5, where n represents a physical term and a sub 1 is the first physical term in a sequence. Therefore, we can say that the domain of n is the set of all positive integers. Remember, n represents the physical term. So we're never going to have the negative third term. We're only going to have the first term, the second term, the third term. Therefore, n represents a physical location in the sequence. So, here's our rule. A sub n equals 2n minus 5. Let's start generating our sequence. So what's our first term? Our first term is going to be 2 times 1 minus 5. That's 2 minus 5. That's negative 3. Now our terms themselves can be negative integers. Even rational and irrational numbers can be our terms. But n is only going to be the set of positive integers. So n equals 2. 2 times 2 minus 5. 4 minus 5, negative 1. 2 times 3 minus 5. That's 1. All the way down, and we can go to n equals 10. We can plug in any value of n that we desire. 2 times 10 minus 5, 20 minus 5, 15. As we progress through the sequence, we have a difference of 2 every single time. And that 2 is representing the difference. Sometimes sequence rules are given in terms of a recursion formula. A recursion formula is when you use the previous term in a sequence to find the next term. So a sub n minus 1 represents the previous term in this recursion formula. So in this example, we're given that a sub 1 is 3. So we know that the first term is 3. And the recursion formula, a sub n equals 3 times the previous term plus 10. So if a sub 1 equals 3, then a sub 2 equals 3 times a sub 2 minus 1. 2 minus 1 is 1. So we will be plugging in the 3 here as it is the previous term. So 3 times 3 plus 10 is 19. Right there. Other things we're going to use in this chapter. Factorial notation. Factorial notation, most of you are familiar with. It is exemplified with this handsome exclamation mark It is on your calculator. I'll show you how to get that. In order to access factorial, it is most easily found, I believe, with this alpha F2 if you have the 84 plus or higher, and it is option 9. So I'll put in 5 factorial, and it's equal to 120. So, by definition, 0 factorial equals 1. This is just something you just have to accept. It is what it is, and it works. Factorials show up in lots of handy formulas that we use in advanced mathematics, like counting principles and probability. So we can easily simplify factorials. I just did that one on my calculator. 5 factorial, which is 5 times 4 times 3 times 2 times 1. That's 120. We can also simplify factorials in fraction form by hand pretty easily, just by canceling out factors that are equivalent to 1. So 9 factorial over 9 factorial, they cancel because they're equal to 1. And then we've got 3 times 4 is equal to 12. 2 times 5 is equal to 10. And here we are left with 11 over 42. So lots of times there's no need to go to the calculator if we'll just stop and think for just a moment and take a good look about what is actually going to cancel. Also in this section is summation notation, also known as sigma notation. And these are all notations that you're going to continue to see in your study of advanced mathematics. And I will definitely put this information on a page in our Google site, so you'll be able to refer to it easily. So here are the different parts. So first of all, this is the uppercase Greek letter sigma. And this sigma notation has a lower limit, an upper limit, and an argument. So lower limit, I equals -1. And this is just I in terms of the index of summation. Other letters commonly used, K, X, J. I imagine there's plenty more. When we do this on our calculator, which yes, we can also do this on our calculator, here's how you get to it. So if I want sigma notation, it's still that alpha F2 again. Go to option 2, and you can plug in all the different parts of a sigma notation here. We'll do one of these a little bit later. So here's what we've got. Lower limit, I equals 1. Upper limit, n. A sub I is the argument or rule of the summation. So let's do an expansion together on the bottom here. So we've got a sigma notation with a lower limit of 1, an upper limit of 6, and our rule is square it, add 2, and then add that particular simplification to the next. So here's what we've got. We've got 1 squared plus 2 plus 2 squared plus 2 plus 3 squared plus 2 plus 4 squared plus 2 plus 5 squared plus 2 plus finally 6 squared plus 2. So that is the expansion of the summation. So we're going to carefully simplify using order of operations. So 1 squared is 1, 1 plus 2 is 3, 4 plus 2 is 6, 9 plus 2 is 11, 16 plus 2 is 18, 25 plus 2 is 27, 36 plus 2 is 38, and then we can add these all together. That's 9 plus 29 plus 65. So 38 plus 65, that is 103, if I did my addition correctly. Hoping so. Let's check it here on the calculator. So once again, that is, and I'll zoom in so you can see it better. So here is what we're plugging in to our calculator. So we have a sigma notation. So here we go, alpha F2, and we want to choose, obviously, we want to choose choice 2, which is the sigma notation. So choice 2, and then we just have to fill in all the parts. So on our variable key, we don't have an I, but we do have an X because we're most likely in function notation. So we're going to enter that in. So X equals 1 for the lower limit, and the upper limit is 6. And then we're just going to fill in our argument. So once again, instead of I squared, we're just going to put in X squared. So X squared plus 2, and then enter, and we get 103. So that's how you enter in a sigma notation on your calculator. So here is an interesting one to take a look at. We have a lower limit of 1, an upper limit of 5, but this time our argument is simply 7. So 7 plus 7 plus 7 plus 7 plus 7. First term, fifth term, all 7s. No variation here. So basically, it's 35. Just wanted you to see that. They're really quite simple to work with. Now, sometimes we're going to go backwards from an expansion. And honestly, I have to think really hard about these things sometimes. These are both pretty simple. You may, in the future, bump into some that are more challenging. So first thing we're going to look at is we're going to look at what is changing and what is not changing. Well, the first thing I see that is changing is our terms. So basically it appears that our term, our base of our exponential is changing with each. And it looks like our lower limit is 1, our upper limit is 20. Now what is not changing is our argument is getting raised to the third power as we continue through this expansion. So, drawing your funky uppercase sigma, and this time I'll go with a J. How about that? So, J equals 1. Our lower limit is 1 because that's our first term, 1. Our upper limit is 20 because it's expanding to the 20th term. And then our argument, J, is getting raised to the third power. That is supposed to be a 3. There we go. Our J is getting raised to the third. And let's go ahead and let's take a look at exactly what this summation would be if we added it all up. And I'm thinking it's going to get pretty large pretty quickly. So alpha F2, go to our sigma notation, and let's fill in the pieces. So X equals 1. 1 is the lower limit. 20 is the upper limit. Our rule or argument here is X raised to the third. And when we simplify, we end up with 44,100, which makes sense because 20 to the third on its own is going to be 8,000. So we've got a pretty good amount in this summation. To the bottom, what's changing, what's the same? Well, across the board on the bottom, we have a numerator that's equal to 1. So what is changing? Our denominators. So I'll give you a little helpful hint here. If you ever see the whole number 1, remember it's over 1. And we could rewrite this and think about it in another way. We could even think of this as 1 over 4 to the 0 plus 1 over 4 to the first plus 1 over 4 squared, 1 over 4 cubed plus 1 over 4 to the fourth. And this is an infinite sum because it continues on and it gives our ending upper limit in terms of n, which honestly makes this ridiculously easy because that's the rule right there, guys. So in order to write this as a sigma notation, it's going to have a lower limit. We'll use x this time, a lower limit of 1, and upper limit of, whoop, I was about to say n and wrote 2. Try again with my handy dandy eraser tape. An upper limit of n, and our rule is 1 over 4 to the n minus 1. Now, one thing to think about here, because what would the infinite sum be? Well, we don't know exactly what the infinite sum would be, but look at what's happening as we continue in this expansion. Our values, as we continue to expand, are getting smaller and smaller and smaller. So essentially, as n continues to get bigger, we are approaching 0. So that's kind of just a nod as to what's coming in calculus. So finishing off here, we've got 3 properties of sigma notation that you need to know about. The first one here, very simple to understand. We have a sigma notation of a product. Now think about it. That C value, it is a constant. That C value is a constant, so we have a constant times our term. All right, so our term is going to be just growing. So C times 1, C times 2, C times 3, C times 4. So we can break this apart. Instead of having the summation of C times A sub I, it equals the same thing as C times the constant times the summation of A sub I, with a lower limit of 1 and an upper limit of n. And I have written the last 2 rules all in one by using the plus minus sign. So the summation of a sum is going to be equal to the sum of the 2 summations. That's a true statement, as well as the summation of a difference will also be equal to the difference of those 2 summations. Of course, order being very important there.